Hello again, this is Dr. James Camp from Lee College in Baytown, Texas, and this is the second part of my commentary on Chapter 4, Loops, from Big C++ by K. Horstmann. We're going to start today with common loop algorithms. We'll talk about nested loops, and we'll talk about random numbers and simulations. These common loop algorithms provide a starting point for your code. You may not always copy them exactly line for line. Or word for word. You may have to change some bits to make them work exactly the way you want them to. Okay, total and average. We've already seen this in my lab session on the grade point averaging, homework grade averaging program. But here goes. You start with a total that you initialize to 0 and a count that you initialize to 0. Then you're going to start taking input, and while cn input operator input is valid, as long as the person keeps typing numbers, you're going to add the input to the total, and then you're going to increment your count, your number of values. That gets you the total. To get the average, you then take the total and divide by the count. Now, in my grade point averaging program that homework grade averaging program that I wrote in the lab, I kind of assumed that you'd have at least one grade. Here, they don't do that assumption. They say if count is greater than 0, then we take average as total divided by count. These two algorithms both do essentially the same thing. They count matches. They both use, the first one uses a for int I equals 0, I less than string dot length I plus plus. So we're going to count through the entire length of a string. And if the one character substring at each given point is equal to a space, then we increment the number of spaces. In the bottom one, instead of incrementing through a string, we're taking input, and as long as input is valid, which since input is string, that's going to be pretty much forever until somebody kills the program, then input.length is going to be if input.length, if the length of the input string is less than or equal to 3, we increment a variable called short words. So that's kind of instead of matching the word, we're matching the length of the word. Finding the first location in a string is a really important algorithm. We start with a Boolean found equals false. So we have a flag variable here that's going to tell us when we find the first space character, and we start with position at 0 because that's the start of the string. Now, you might think that in counting through a string, we'd want to use a for loop, but in this case, we want to terminate as soon as we find the correct position. So we're going to say while not found and position is less than string.length. We're going to find the one character substring at the current position. Then if that character equals a space, then found equals true. We're done. Else, we increment position 1 and go through the loop again. The loop will end if either we find the character, in which case position will be set to the position of the space, or if position is suddenly equal to string.length, in which case we know that there are no spaces in the string, and position will be set to the length of the string, and that's an indicator that there is no space character. There are no space characters in the string. Another common loop algorithm is prompting until the input is valid. Okay, so we start by assuming that valid is false. We haven't had any input yet, so obviously the input is not valid. And then we declare an input variable before we get to the loop so that it will persist after the loop. While not valid, we prompt them for a positive value less than 100. So we want to be between 0 and 100. We take input, and then if 0 is less than input and input is less than 100, our input is valid and we'll exit the while loop. Else, we see out invalid input, and then we enter the loop again and ask for another positive value less than 100. Min and max, we also saw this one in my homework grade averaging lab program. You start with the largest and smallest variable, then you declare an input, and you take the first input outside the loop so that you can set smallest and largest to both be equal to your first input. Because when there's only one entry, it's both smallest and largest. Then while cn gives us valid input, if input is greater than largest, we set largest to input. If input is less than smallest, we set smallest to input. And by the time we exit that while loop, largest will now be the largest input that we got, and smallest will now be the smallest input that we got. Another possible use of loop algorithms is to compare adjacent values. We have to have an input, but in this case, we have to have a previous and a next. Okay, so we take the first entry outside the loop to become the first previous input, and then while cn gives us valid input, if input equals previous, we see out duplicate input, and then previous becomes the current input so that the next input can be compared to its previous. It may occur to you that all of these, each of these common loop algorithms could easily be turned into a function, that you could create sort of a function library of handy loop algorithms. And in fact, a few of these algorithms are already found in the algorithm header in the C++ standard library, but most of them are not. So, it might be worth it for you at some point to write your own library of common loop functions that you can then copy and paste into whatever programs you're writing. Okay. Now our author has some general advice on how to write a loop. The first step is to decide what has to be done inside the loop. Okay, are you reading another item? Are you updating a total? Then you have to specify the loop condition, and that helps you figure out the loop type. Okay, if you're exhausting a count, then you're probably using a for loop. If you're looking for a condition like invalid input, you're probably using a while loop. And you're going to set up the variables for entering the loop for the first time. For loops often don't have any variables that need to be set up because the counting variable is part of the for loop definition. But while loops always have to have their conditional variable defined before you get to the while loop. You're going to process the result after the loop has finished. And then, as per K. Horstmann's perpetual suggestion, you're going to trace the loop with typical examples before you write it in C++ code to make sure that the loop that you've written on paper will translate into good C++. Here's an example, credit card simplification. much of the time when somebody writes a credit card number in a credit card field on a web commerce form or something, they put dashes between every 4 digits, or maybe they put spaces between every 4 digits. We want to simplify that into just a string of 16 numbers so that they can more easily match what's in our database. So what work must be done inside the loop? We need to check each character of a string, and if it's a space or a dash character, we want to remove it. The loop condition is that we're going to keep going until we reach the end of the string. The loop type, well, at first this looks like a for loop because we're counting till the end of the string, but it turns out a while loop is better for this situation because we're going to keep removing characters from the string, so the length of the string is going to change. Also, if we remove a character from the string, we're not going to be plussing the position, so that screws with the mechanism of a for loop. We can set up variables for entering the loop for the first time. We need to define a credit card number as a string. And then we need to process the result after the loop is finished. In this case, we're just going to output the credit card number. We're going to trace the loop with typical examples, implement the loop in C++. Well, we're going to skip step 6 here and look at what step 7 looks like. So you start with your credit card number. While index is less than credit card number dot length, we're going to find the 1 character substring at I, at position I. If it's a space or a dash, we're going to concatenate the substring before the dash and the substring after the dash, and that effectively removes the dash from the string. If the character is not a space or a dash, then we want to I++ and move on to the next character. Okay. Another interesting situation with loops, that's my dog in the background, is nested loops. Just like we did with ifs and elses, we can nest loops, one inside the other. Okay. One use of nested loops, as shown at the right, is processing data in rows and columns. Another use of nested loops, which we'll visit later in the course, is sorting lists. For example, this is a pretty inefficient list sorting algorithm, but it works. For I is 1 to list.length minus 1. Then for j is I plus 1 to list.length. If list at I is greater than list.j, we swap the values. By the time you've processed the whole list, essentially twice, you will have, or n squared times actually, you will have got all your items in order. Okay, the flowchart at the right prints a table of powers x to the n. The outer loop is going to run down the rows, one value of x for each row. The inner loop is going to run across the columns, printing x to the n for a different n for each column. The output should end up looking like this, where your outer loop is counting down the rows, and your inner loop is printing across the columns. Why do we have them in that order and not the other order? Well, because output in console output has to print one line at a time. We can't print one column and then go back up and start again with the second column. So we have to go across first and then down on the outer loop. How to write a nested loop? We want to have 4 columns, and in each column we want to print x to a different power. Okay, so let's write the inner loop first. It's going to look like this: table row equals x. For n equals 1 to 4, print x to the n. So we're going to have 4 columns going across. We can test that this works before continuing, because if you can't correctly print one row, why try printing lots of them? For 10 rows, we now add an outer loop for x equals 1 to 10, where table row equals x. For n equals 1 to 4, on the inner loop, print x to the n. And then at the end of each row, we're going to print an end of line. This is what that looks like in C++ code. Much less easy to read than my example in pseudocode. But you can see here that this is printing the table headers. This will print the letter X under the table header to show you that you're getting X to the N. I just added that. And then this is the actual, here's your outer loop, here's your inner loop. That's the actual nested loop part right there. Some more nested loop examples. This one is going to print a triangle of stars. That was one of your homework assignments from when we first introduced loops. The way this one works, the outer loop, I, goes from 1 to 4. The inner loop goes from 1 to I. So it's a different, the inner loop goes a different number of, prints a different number of stars each time depending on what the value of I is, which row it's on. Very clever, right? What does the following code print? Well, the outer loop takes us from 1 to 4. The inner loop takes us from 0 to 4, 0 to less than 4. So it takes us from 0 to 3. And we're printing 10 times I. So we get 10 on the first row, 20 on the second row, 30 on the third row, 40 on the fourth row, and then we're adding J. So going across, we get 10, 11, 12, 13, 20, 21, 22, 23, and so on. Another example is image processing. Each digital image, as you may know, is made up of tiny squares of color called pixels that are arranged in rows and columns. So just as with printing a table of values by rows and columns, we can print we can do image processing by rows and columns. And so here, once again, you have an outer loop that handles X from 0 to width, and then you have an inner loop that handles Y from 0 to height. And then the particular processing they do inside, in this case, they're inverting the image, but you could do any number of things with that image. You could brighten it, you could increase contrast, you could do all sorts of things. But the basic structure is that you have to be able to go through every line and every column, every X and every Y. All right. Finally, shifting gears completely, we're now going to talk about simulations. A simulation program models an activity in the real world, or perhaps in an imaginary one. Most video games today, all of the kind of immersive world video games from Minecraft to Fortnite to Grand Theft Auto, these are all simulation programs. They simulate an imaginary world, and then your character plays around in that imaginary world. In fact, one of the most popular games out there is called The Sims. It's a simulation game. Um, Commonly in the real world, simulations are used for predicting projectile paths. This was the very first application of a real computer, ENIAC. Today, we use these to use computer simulations to predict how satellites are going to travel in space and um, how space debris might collide with the International Space Station, all sorts of interesting projectile path problems. Forecasting simulation programs are used daily by the National Weather Service to forecast your weather. A little more critically, they're used to forecast hurricanes for our Gulf Coast region here. Um, and they're used to calculate climate models, to calculate on a much longer time scale, what's going to happen to our climate as global warming continues to happen. They're commonly used for analyzing traffic. You can simulate cars leaving traffic lights and try to optimize the traffic flow in a downtown area or something. They're used for optimizing resource use. There are models that can look at how efficiently the processors on a computer are being used, or how efficiently the gas pumps at a gas station are being used, or the cash registers at a checkout line in your grocery store, or any other number of resources that have a limited number of resources and lots of people trying to use them. There are simulations of the stock market that can be used to try to pick which stocks to buy. There are many other applications in science and business. Since things in the real world happen at random times and with random amounts, within a certain range, we need to generate random numbers for our simulations to seem real. Okay. As a result, almost every programming language out there has a random number generator. Most of them are pretty bad. The C++ standard, or the C standard library, provides the rand function in the C standard lib library. And it's a pretty poor random number generator as RNGs go. It's not any worse than the one in, say, Java or the one in C#, but it's not nearly as good as the random library that's provided as part of the C++ standard library. You can go to cplus.com/reference/random to get a full discussion of how all of this works. But the basic idea is that there are generator objects that produce very large random integers. Okay, default random engine is not a whole lot better than rand from the C standard library. It's a little bit better. But there are some other ones like the Mersenne twister and some other things that I use for professional simulations for my research that are much, much better random number generators than what you get from the C standard library. Once you've picked a generator object, then you pick a distribution object. Okay, you can get a uniform int distribution that, for example, if you choose a uniform int from 1 to 6, you're essentially simulating a dice roll. You can also get a uniform double distribution that will, same thing, you span 0 to 2, say, and it'll give you every lots of very small numbers from 0 to 2, including 0.04325, 1.267, whatever. You can also generate a normal distribution. This is probably the second most commonly used, is that you want to simulate a population that has a bell curve distribution, because most populations out there are not actually uniformly distributed. Most things are not really like a dice roll. Most things are more like a normal distribution, that classic bell curve. Okay, they've got a mean, an average value, and they've got a standard deviation, the width of the curve. Rand and default random engine are both what we actually call pseudo-random. They follow algorithms that produce a series of numbers that look random. Okay, they are not related to each other, and they're not in any kind of sequence, and they don't repeat for a very long time. But they all have to start from somewhere. And if you don't provide a starting point, they will always pick the same starting point, which means you'll get the exact same series of random numbers every time you run your program. To prevent that, we seed the program, we seed the distribution, and the most common way to do that is to use the time. Because the time, it is a change-in. Okay, thank you, Bob Dylan. An easy way to get the time is to call the time function from the ctime header. You pound include ctime, and you call srand of time of null, and that seeds the random function with the current time of day in seconds since 1970. So it's a rather large number, but it's a constantly changing number. The C++ random number generators are slightly more complicated. You declare a default random engine variable. You call it something. I like calling it randgen. And then in parentheses after the variable name, you pass it a seed, time null. Okay. Here's a dice tossing example. We seed random, and then for 1 to 10, we're going to do 10 dice rolls. Dice 1 is rand %6 plus 1. Dice 2 is rand %6 plus 1. So we get two random numbers between 1 and 6 inclusive. And then we print out the two dice rolls. Okay. Another simulation example, a more complicated one, is something called the Monte Carlo method. When it turns out to be hard to calculate a value, but you can get at it by randomly approximating a bunch of trials, as if you're perhaps doing a bunch of random real-world experiments, and then you tally the averages. For example, we can approximate the value of pi by simulating shooting a dart into a square surrounding a circle of radius 1. Okay, we get random x and y coordinates between -1 and 1. The dart hits inside the circle if x squared plus y squared is less than or equal to 1. Remember, the classic equation of a circle is x squared plus y squared equals 1. Because our shots are entirely random, the ratio of hits to tries is about equal to the ratio of the circle and the square. The area of the circle should be, the area of the circle divided by the area of the square should be pi over 4. Therefore, our estimate for pi is 4 times the number of hits divided by the number of tries. And this is what that looks like in code. This time I chose to use the C++ random library. So we got a default random engine, which we seed with time of 0, a uniform real distribution of type double from -1.0 to 1.0. We initialize hits at 0. We're going to do 10,000 tries. If we have more tries, we generally get more accuracy, but it's obviously takes more computer time. And then for I equals 1 to tries, we get a random x and a random y, and if that point is inside the circle, we increment hits. Then our pi estimate is 4.0 times hits over tries, and we print our pi estimate. I encourage you to copy this code and paste it into your web browser, and paste it into your C++ compiler, and see what kind of numbers you get for pi. It won't be exactly 3.14159, and it'll vary each time you run the program. And you can try varying the number of tries and see if you get more or less accuracy. Okay, so that brings us to the end of this week's presentation. Um, some loop applications practice. Um, a string separator program. I want you to take a string with spaces as input from the user. So you're going to do a get line and read a string with lots of spaces in it. And then using the find first location algorithm from this lecture, you're going to find the first space in the input string. You're going to print the substring before the space, followed by an end line. Then you're going to replace the input string with the substring after the first space and repeat these steps over and over again until you've essentially separated the string into each word that it contained and printed each word on its own line. A little bit more complicated challenge for those of you who are up to it is a Monte Carlo practice. You're going to set up a random number generator to produce double type floating point numbers from 0 to 2. Okay, instead of -1 to 1 like we did in the example just a moment ago, you're going to do from the range from 0 to 2. You're going to generate, say, 10,000 random numbers, and for each, if random times random is less than or equal to 2, you're going to increment found. Okay, that is, if random number squared is equal to 2 or less, we're going to keep that result. And the output should be found, the number of hits, divided by 100,000 times 2, times the range from 0 to 2. And that should come close to the square root of 2, which is 1.414. For a little more complicated challenge, try making it so that the user can type in which number they would like to find the square root of, and your program does that. Okay. Until next time, good luck and happy programming.